defining with what I mean with schematization. I'm going to use about 1,000 words for that. Hopefully most of you will recognize a sheep here that is chewing on a flower. Right. One thing you might also notice, this is not a sheep. This is just a couple of lines showing you a representation of a sheep that you would recognize. And it's not photorealistic, but it's enough for me to convey to you what I want you to see. So that's schematization real short, but I'm going to use it to do something other than making cute cartoons. Instead, I'm going to be talking about cartographic schematization, which is about making maps, essentially. And the idea there is that in a schematic map, you focus on what's important for the map. And in many, many cases, this is actually not very precise geography. So we're going to focus on the functional design. This is a railway map of the Netherlands, in a small cutout of it. And what you'll see is that all the lines are nicely under 45-degree angles, or horizontal or vertical. But I can tell you the cities and towns in the Netherlands don't line up that nicely. They've been warped just so you can read the connections more easily, and it focuses on the purpose of the map. You'll also see that the same has been done to just the shape of the Netherlands, and that's actually what I want to focus on in this talk. The reason is that this is actually useful for a lot more things than just transit maps. In particular, they can be very useful for showing data that is uncertain or inaccurate in some way. So here's a map that was shown to, was drawn to show water stress levels as forecasted for 2020. It's a bit of an old map, but sure. The idea is that by not using a very precise map, you can still give a very general overview and structure of what is going on, but is not suggesting that the data is very accurate. And this illusion of accuracy could happen if you would show such kind of data, which can be very inaccurate and uncertain, right? It's a prediction for, at that time, roughly 10 years ahead. It's not allowing you to make very precise calls on what the data is showing you. It focuses on the overview of the structure. Similarly, there's a class of maps that are called chromatic diagrams even, so they're not even calling it maps at this point, but they're also using very abstract stylistic depictions of regions, countries, and so forth to show you high-level trends in this case, geographic analysis. So in this case, I mean, you have Brazil up here, Vietnam, for example, Argentina, and I believe that's one of the regions in India. But the stylistic representation helps you to abstract away from the nitty-gritty details of geography, and you focus on the high-level structures instead. So to talk a bit more about Odin, because of course that's why we're here, let's define a problem. So the schematization problem, there's many ways of formulating it, but one high-level way is to say, well, we want to compute a stylistic shape, given, let's say, the outline of China or some other kind of region. We want to compute a stylistic shape that resembles the geographic one. So something like this. Of course, if you want to do algorithm, this is nowhere near precise enough of what we want to do, so let me roughly define it in a bit more precise way. Input a simple polygon. Countries don't tend to intersect themselves. So we have simple polygons and a set of angles. And the angles here in this example are multiples of 60 degrees. It's kind of capturing this idea of stylistic. And the output, we want to get a simple polygon. We wanted to use few edges. We want to make sure that all those edges adhere to our set of angles. And we want to make sure that it still looks like the original shape. But it doesn't have to be precise, right? So there's some bound on what we want to achieve there. And actually for this talk, I'm mostly going to be focusing on the simplicity of both input and output and the similarity metric. So a set of angles, I mean, this is part of the input, but the reason why I'm not going to be talking about it as much explicitly is because I want to take a discretized approach. The idea of that is that I take this shape and I just overlay it on some kind of grid that captures my stylistic desires in that sense. So in this case, if I want to do a hexagonal schematization, such as here, I overlay it on this triangular grid, and then the only thing I need to do is find a path in that grid, or graph if you will, and that is then my schematization, and I'm done. So the only thing I need to do is fill in this little blank with some magic, let's say an algorithm, that does this for me. Before I go into that, I want to sort of motivate why I think this is useful to begin with, because by using this discretized approach, I'm limiting the potential solutions, right? Because I want to have a simple polygon, I'm really restricting things here. I mean, even without simple polygons, there are just some shapes that I cannot make that are still hexagonal, but I could make in the general plane. So for this, I think there's a couple of motivations for it. So first of all, well, if I use a grid, maybe it's not a tiling, but I can use it to capture all kinds of stylistic constraints, a bit more than just a set of angles. For example, here's a schematization of Russia that is using concentric circles and spokes, if you will, focused on the North Pole, or more like an isostatic schematization, which I haven't seen, but I thought was cute that we could use this for, to make all kinds of, for the same reason, because we're using this grid, actually all the edges, if you have a nice grid that is, all the edges, they are better aligned. They're not just randomly placed in space, if you will, and they're more uniform. So if you start schematizing multiple shapes, to look for illustration purposes, use letters there, it gives a stronger sense of schematization, also a bit more of a coherent look and feel, actually, if you're schematizing multiple shapes at the same time. And the third reason, this discretization forces us, if we want to have a simple polygon, to have a minimal width everywhere in our polygon. Right? So if we have Thailand over here, then this very narrow stretch of country here, it needs to have a minimal width corridor in the grid we're using. Whereas if you use other techniques, you could sort of get a visual collapse, which is kind of pretty much just a line that you're seeing there. And if you would draw this in a constellation of multiple regions, you might even think that these are two different regions because they don't appear to be connected anymore. As a final reason, it can actually sometimes also, just from the use case for your map, be useful to be able to have this discrete schematization. So on the left is a mosaic map, so all the, it's a cartogram, all the regions have been scaled according to some data value. Just a very typical map, we'll use elections here. But it's an integer data set, and you can really count the data that is in there by just counting the number of squares. And actually, to make this map, one of the sub-steps in that process is solving one of these discretized schematization problems separately for all the regions. It can also be used for what is called maybe more a grid map. So here's again Thailand as an example, where every region is just represented as a square, and they're packed together to make a region that roughly looks like Thailand. There's all these kinds of reasons for why this discretization is useful, but the main question, of course, for us is how do we fill in this small step that is called magic? So the problem we're looking at is, in this paper, is actually going to be using square grids mostly, but some of it also generalizes to hexagonal grids, like here. But it also, I've been talking about similarity metrics very generally, but we need to choose something, right? Otherwise we can't really compute or work with it. And there's some couple of usual suspects. I mean, there's a lot more similarity metrics that you can think about, but these always pop up on my list at least. I'm going to fill this table of what we kind of know and what we now know bottom up. So I'm going to start with the Hausdorff distance, and because it's a fairly simple metric, you might think, well, that's a good way to start. We don't have any new results here because there was already results known. So we know that if you insist on a simple polygon as an output, even if you have a simple polygon as an input, then this is an NP-complete problem in general. But in the same paper, we also showed that if you're given a simple polygon, there is always at least a grid polygon that has Hausdorff distance at most 2 points and a little bit. So you can get quite close, but actually minimizing the Hausdorff distance is where it turns hard. And this is actually the Hausdorff distance for both boundaries and interior versions. But let's continue on. For the symmetric difference, there's a very simple greedy algorithm if you don't care about whether your end result is connected. But what we show is that as soon as you enforce some kind of connections, then this problem turns out to be hard. And I'm just saying connected because it doesn't really matter whether you want to have a polygon with or without holes, both variants are actually NP-complete, as we show. And even if we insist on area preservation, so you're given a polygon and you want to make sure that the schematic version that you're computing has the same area as the input polygon, or even some other target area that doesn't really matter that much. So, hard problem. So you would think maybe the Fréchet distance offers help, but it doesn't really get better there. What we knew is that there is a polynomial time algorithm if you don't insist on simplicity of our output, and it's not just one of those, by the way. There's general algorithm has this 3D algorithm also is. What we also know that if your polygon is beta narrowed, so kind of realistic input model, then similar to this result, you can bound the maximal Fréchet distance that you need using these beta. But it's quite a generous bound. What we show here is that this problem is actually also FP complete, and even that you cannot get a p-task unless P is MP. And again, this is also if you're willing to assume area preservation or some kind of polar area requirement is still no p-task, and even if the terms are given. So we saw Stefan Langerman talking about this boundary representation of the polynomials. It's kind of the same idea. So if you have some oracle for this problem that tells you, well, your polygon should have the following sequence of turns, where you want to turn left, then 2 times right, and another left, and so forth. Even if someone is telling you that, you still cannot get a p-task. So this is an annoyingly hard problem. So just very briefly on how this works. So the problem first I'm going to talk about is the Fréchet distance variant. I'm not going to define the Fréchet distance. You might have just seen it in Tim Ophelder's talk. But the main thing you need to know is with the Fréchet distance, you kind of just have to follow your input polygon quite closely. We're going to see whether it's hard to find in this black grid a simple cycle such that the Fréchet distance is at most 3.5. Well, it's an empty hardness reduction and it's geometry, so usual suspect, you might think, let's reduce from something very original like planar monotones or something. Right? I've never seen it before, it's very unique. Yeah, I'm not going to say too much about this. You have some variables here, and you have a formula that you want to check that's satisfiable, that's represented by these clauses. And well, we're using the monotone variant, so that means that all the things here are unnegated and all the things below are negated. But we don't actually need that, it just makes it simple. Okay. So that is what we reduce from, and what we do is essentially make the same structure in our grid and polygon. So we cannot choose the grid, of course, but we can route our polygon. And it roughly looks like this. So these black boxes are the gadgets they would expect in a very typical reduction. And the rest is the boundary of the polygon that we're constructing. Roughly, it's a schematic of how to make schematic. So these things are, again, the variables, and the yellow things up here and below there are the clauses, and that kind of all works and it communicates. And mostly what you would expect, I mean, these things in communicating, you just wiggle a lot and wiggle a lot, and you have to constantly follow that, so that kind of works out. The only thing that's a bit more complicated are these clauses, and I'd like to show it to you. So this is the construction. The only thing that is actually being used is the red curve. It's like a piece of the polygon. The rest is just reason about it. I'm not going to explain why this works, but I just want to show you a couple of pictures of kind of how it works. So the idea is that you have the 3 edges in the embedding of the formula that are being attached to these light green ports. And then, well, there's a way of finding a curve within this black box that kind of just touches one of these green things. And that's just saying, that variable is the one that's going to satisfy this clause and is satisfying the sign. And well, we have 3 of them. But in particular, there's no curve really within the black box that doesn't touch either of them. Right? So there's always one variable that has to be true. The nice thing here is if you sort of flip through it, it might be a bit difficult to see because it's all very nested, is that no matter which one of these 3 I choose, the bends that I'm using are the same. So this is how we get to this idea of even if you have this oracle, that doesn't help because we could very easily find a sequence of turns based on our construction that we would be able to use if there is a solution. Okay, so back to this overview. The only thing I really want to mention for this introduction at the end is how we get to the area preservation. And well, that is also quite a simple idea. This thing will tell you whether it's satisfiable, and we kind of append something to it that is the exact same thing. So whenever in the other thing something area is added, you can use the same embedding on your grid here that will remove the same area because the inside and outside have been inverted. So you get area preservation. Right. So that was it for the Fréchet distance. How am I doing on time? So for the symmetric difference, same problem, same picture. Now we want to select a set of cells that are connected and have a symmetric difference at most something. And if I take such a thing, the symmetric difference is really just this red area. So if we overlay the two, it's the area that's covered by one of the polygons, but not by both. Here we actually could do something a bit more original, and it's not reduced from planar tree set, but we were using minimal rectilinear Steiner tree. So we're giving a set of nodes, these black ones, you want to connect it with a tree using only horizontal and vertical lines, such that the length of this tree is minimized. This is a known empty complete problem. And what was already shown by Hanan quite a while ago is that this grid here is something that should contain the minimum solution. Right, I mean, there's also other solutions possible, but this grid will also contain at least the variant. So while we have a kind of a grid graph there, so we convert that to a grid, and all these red hashed areas are just the faces in the grid on the left, the black ones are the nodes, the white ones are the white nodes, the ones that don't count, that you don't have to connect, and the grays are the edges. So the only thing that's left to do is sort of think about how our polygon that we need to construct as an input is going to overlay these pieces. And the red ones are going to be completely blank, and for the others, so we have some kind of a translation scheme, it's just a one-to-one mapping. So for the white, it shouldn't have any cost, right? They have zero length there. So what we do is we cover it by 50% of the area of the unit square, which means in the end, for the symmetric difference, it doesn't matter whether you select it or not. And if you select it, you cover 50% too much. If you don't select it, you cover 50% too little. So for the nodes, we kind of fill them all the way completely, which if we set our threshold for the symmetric difference carefully, will just mean that these have to be covered by the cells you're selecting. And the gray ones, well, they kind of vary in how much we cover just to encode the edge limit. With such a translation scheme, what we get to is something like this. And, well, you kind of have a one-to-one correspondence between the length of the rectilinear Steiner tree there and the symmetric difference on the right. So it is a problem in that department. Area preservation is not too difficult, but I wouldn't be talking about it here. Rather than that, we have all these negative results about, this is hard, that is hard. There's a bunch of things that we want to go further with, and I'll just leave it up for you to read. I think, so we have been thinking about these, especially also for symmetric difference from approximation, where since the last week we think we know how to do below 3, but there's some details to be verified. And with that, I'd like to close. Thank you for your attention.
Any questions for our speaker?
So what's known in terms of related work where you're not bound to the grid, but you have an upper bound on the number of set edges? You're still required to follow specific angles for your edges.
Yeah, there's quite a lot of work there, but a lot of it actually doesn't require you to get a simple output. So if you're willing to tolerate intersections, then there's a lot you can do. And there are some very nice algorithms known already from quite a while back. I'm not aware of actually algorithms that do this optimally in any sense without introducing intersections. Would also be a very interesting motivation. So when I started this, I figured by discretizing it, I get a bit more of a grip on this problem, makes it easier. It just turns out that it doesn't. So it would also be another venue to explore it.
Any other questions?
What do you mean by the necessary local deviation?
Yes. So the Fréchet distance is something that is characterized by where the distance, when you're sort of doing this walk, wherever the 2 points are furthest apart, that is what is determining the Fréchet distance. So if you have a polygon that somehow forces you to have a huge Fréchet distance in one part because it's wiggling all the way, but you could very nicely follow it on other parts, then because this bottleneck is just saying, well, the Fréchet distance is huge here, if you don't pay attention to it, I mean, this very nice part you could follow, you could also start doing anything just because it's still within the Fréchet distance. So if you're trying to really make maps this way, you have to take care of this issue here. You want to make sure that you're not unnecessarily wiggling around it and you don't have. Okay.